Hello, Absolute Mathman here. Today we shall discuss dice simulation. That is, how to replace dice with other dice. For example, if you wanted to play a game that requires a 20-sided dice, such as Dungeons and Dragons, but you only had, for example, a D10, a 10-sided dice, and those regular 6-sided ones. Or even worse, if the D10 didn't exist, and the only thing you would have is these regular 6-sided dice. Question is, how would you replace the D20 with the dices you have? Let's start from a simpler case. Let's say that we want to generate a random number from 1 to 4. That would be given by a tetrahedron shaped D4. But let's suppose that we don't have such a thing, or for some reason we don't want to throw it. And instead we want to generate the random number by throwing this 8-sided dice. So we mark the number given by the 8-sided dice with X, and we want to transform it into an other random variable Y, which is a uniformly distributed random number in 1, 2, 3, 4, so it generates a number 1, 2, 3, or 4, which should be equally likely. So how are we going to do that transform? If you want to try it on your own, you can pause the video and then continue watching. I will now show you the solution. Or there are many ways of doing it, but one way in transforming the D8 into a D4 is dividing the X, the number given by D8, by 2, and then taking a ceiling function. Well, what does this ceiling function do? It rounds up this number into the next integer. Well, for example, ceiling function of 1/2, it equals 1, because the least integer greater than or equals 1/2 equals 1. And, for example, the ceiling function of 2 equals 2, because 2 is greater than or equal to 2. So let's throw for some insight. So we got a 4, and we see that 4 divided by 2 is 2, and the ceiling function of 2 is 2, so we have actually thrown a 2, and we can actually mark this here. That's a 2, and let's throw again. 8. Well, the 8 divided by 2 is 4, and the ceiling function of 4 equals 4 as well, so we actually threw a 4 here, and for the rest of these numbers, the ceiling function of 7 divided by 2 is also 4, and if it's 5 or 6, we would get a 3 as the value of Y, and 3 would give a 2, and 2 and 1 would give a 1. And of course, the fact of whether or not this is uniformly distributed, well, X has 8 equally likely outcomes. Each has the probability of 1/8, and as we can see, there are 2 values of X for each Y, which gives it. So the probability of each value of Y is 1/4, as it should be. Okay, get ready for this time's problems. First, we ask how to simulate a D20 by rolling a D10 and a D6. That is, how do you generate a random number from 1 to 20 so that each outcome 1, 2, 3, 4 and all up to the 20 are equally likely? By rolling a 10-sided dice and a 6-sided dice. How do you transform them into that random number? And second, we ask how to simulate a D20 by rolling D6 dice only. If you want to try the problems now, you can pause the video, and after you're ready, continue watching to see some ways to solve the problems. Now, before going on to the problem of how to replace a 20-sided dice with a 10-sided and a 6-sided dice, and furthermore 6-sided dice only, we are first going to discuss some number theory related to it. So why it was so easy to simulate a d4 with a d8 dice? That's because 4 divides 8. That means since 4 divides 8, the 8 outcomes from d8 are easy to divide into 4 groups. Equal. But what if we had a d6, a regular dice, and we wanted to simulate a d4 with that? Well, these 6 outcomes cannot be equally divided into 4 groups, which means that in all simulations of d4 involving d6 may require 2 dice rolls. And in a similar way, if we wanted to simulate a d2 2-sided dice with a regular 6-sided one, even though 2-sided dice do not exist, it is easy to do that because 2 divides 6. We can distribute the 6 outcomes into 2 equal groups easily. This way. And in general, if m, a positive integer m, divides n, then an n-sided dice is easy to use in order to simulate an m-sided dice with 1 roll. And now let's discuss the division algorithm. So let's consider that n is a number between 1 and 20 and is an integer. That means that n minus 1 is an integer between 0 and 19. Now, according to the division algorithm, there exists a unique pair of q and r such that n minus 1 is equal to 10 times q plus r, such that q is a integer between 0 and 1 and r is an integer between 0 and 9. The fact that if r is between 0 and 9, we get this in a unique way comes from the division algorithm itself, and the fact that q is between 0 and 1 can be deduced by saying that if q were 2 or greater, this would be 20 or greater, and if it were negative, then this one would also be negative. So, because there is a unique representation of this number as the pair of 10q plus r, it means that the 10 possible outcomes of the d10 and the 2 possible outcomes of the d2 and each combination of 2 of these possible outcomes can be uniquely mapped into each number between 1 and 20 this way. We just subtract 1 from these numbers to make these 0 and 1, and these numbers to be 0 and 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So in problem A, we have a D10 10-sided dice and a D6 regular 6-sided dice, and we want to simulate a D20. So now first we see that the problem would be easier if we had a D2 and D10 instead of a D6 and D10. So how could we replace the D6 with a D2? Well, as mentioned earlier, D6 can be easily replaced by D2 since 2 divides 6 by simply dividing the possible results of the six-sided dice into two groups. So we will make a function if, so that fx2 is, we will also make the minus one thing so that we will directly map into numbers 0 and 1 just to make the future things a little bit easier. So 0 if x2 equals 1, 2 or 3, and 1 if x2 equals 4, 5 or 6. And now with the previous division algorithm trick, we can now write a uniformly random number between 1 and 20 by 10 times fx2, where fx2 is a random number between 0 and 1, and x1 minus 1, we had to take this minus 1 because we wanted a random number between 0 and 9 to make this work, and then we have the plus 1 here. So now we get, when we simplify this a little bit, we get just 10fx2 plus x1. So what this means, let's roll for an example. So I rolled a 3 from the d10 and 5 from this one. So the 5 is mapped into a 1 if this f function. And when we multiply that by 10, we get 10, and x1 is 3 in this case. So we have rolled a 13. Let's roll again. Now we rolled a 6 and a 5. 6 is mapped into 1 again in this fx2. So we get a 10 from here, and 5 gives us x1 equals 5. So in this simulation of d20, we just rolled a 15. Simulating a 20-sided dice by only using 6-sided dice is a bit trickier, but we can do it by simulating a 4-sided and a 5-sided dice. For example, by using 6-sided dice and then combining these two results. So now we can think of this green and this blue dice, so that this green one simulates the d4 and the blue one, the second dice, simulates the d5. So how is that d4 simulated? By a d6? Well, that may require 2 dice rolls, since 4 doesn't divide 6. But we can do like this. If I throw it this first time, and the result is 1, 2, 3 or 4, then that is the result of the d4 5 dice roll. However, if I throw a 5 or 6, then I need a second throw, and 5 would mean 1 or 2, and the second dice roll would then determine the final result, whereas 6 would be 3 or 4, the second roll determining whether it's 3 or 4. So we would write f, where f turns the 2 dice rolls of the first green dice into a d4 result. It shall be like this. So this would be one way to write the function f, transforming these x1 and x2 into a d4 result. So if the first roll is 1, 2, 3 or 4, we don't need to throw again, and we have the final result immediately. But if it's a 5, then it will become a 1 or 2, where 1, 2 or 3 from the second row would transform it into a 1, whereas 4, 5 or 6 from the second row would give a 2. And lastly, 6 will become 3 or 4, and a 1, 2 or 3 from the second row would give a 3, whereas 4, 5 or 6 in the second row in this case would give a 4. However, simulating a d5 with a d6 dice cannot be bounded in a very good sense. That means you cannot bound the number of throws required. So you have to do this. You roll the blue dice until you get a number that isn't equal to 6. In this case, I threw a 1 from this simulated d5. And this time I threw a 3. But now that I happen to roll a 6, I have to throw again. And now I roll a 2, which is a valid result. So in this case, I rolled a 2 from the simulated d5. So we could write a function g that transforms a sequence of d6 rolls w1, w2, into a random number between 1 and 5, this way. It is equal to the first roll if the first roll isn't equal to 6, and if it is equal to 6, it gives the same function result started from the second roll. That means basically throwing again if the first roll is equal to 6. And finally, the random variable y, which is supposed to be a random uniformly distributed number between 1 and 20, we can write it as 5 times f x1 x2 minus 1, because here we had to have a number between 0 and 3 rather than a number between 1 and 4, plus g w1 w2 minus 1 to make it a number between 0 and 4 rather than between 1 and 5, and plus 1. And when we simplify this one, we will get 5f plus g minus 5. So let's take some example rolls. Let the green one be the d4 here, or the simulated d4, and the blue one the d5. So let's roll. The blue one is 3. That's fine, we don't have to throw it anymore, but this is 6, we have to throw once more. The second roll of green was 4, which means, according to the definition of f, that the f x1 x2 will be 4, since the rolls were 6 and 4. So we rolled a green 4 and a blue 3, which will give us 18. A pretty good roll. Let's throw again. This went off screen, but green one is now 2 and blue one is 1. So we rolled a 5 times 2 plus 1 minus 5, which means that we got a 6. So now you've learned some dice simulation, And by generalizing the idea in this video, you can generate a random number in pretty much any range of positive integers by using any dice you want. If you're interested in more math, please subscribe to my channel, and thanks for watching.